These are the notes on nuclear fission and nuclear fusion. Again, we are talking about atomic stability throughout this course, and when we talk about nuclear chemistry, we are looking at ways that our atoms can become more stable. Stable atoms have forces that are between their protons and neutrons that are balanced, and unstable atoms or radioactive atoms are atoms where the forces between protons and neutrons in the nucleus are unbalanced. And so again, we're looking at what is happening in the nucleus to kind of reach a more stable atom. We already talked about types of decay: alpha decay, beta decay, and gamma decay, where particles release or decay off a different type of particle to become more stable. When we are just looking at mass and energy, the total amount of mass and energy remains constant throughout the whole universe. So energy can be converted into mass, and mass can be converted into energy, which is our E equals mc squared, where E is energy and m is mass, c is the speed of light. And so if mass is released, we can release energy and vice versa. So let's discuss nuclear fission, which is a nuclear process. What is nuclear fission? It is when one larger atom that is unstable gets split into two smaller atoms. This is usually caused by adding a neutron to the original atom. And so if we had a larger atom, a neutron got added, then it is going to cause that larger atom to split into two atoms that are smaller and that are more stable. And this process of fission emits enormous amounts of energy in that splitting. And so we see this with elements that have masses over 60, so a lot of our large elements. And just as an example of how we can use this, or how we can how this energy gets produced, a mole of uranium-235, which is about a half a pound, releases 1 billion times more energy than a half a pound of coal burning, which is 2.1 times 10 to the 13 joules. And so when we're looking at fuel sources, we can consider burning things like fuel and gases, but we can also look at using nuclear fission to produce energy as an option. And so a model of fission here is where we have, again, that one larger atom. In this case, it is uranium. And that is splitting into smaller atoms, and it can split into 2 or 3. This is splitting into krypton 92 and barium 144. Sometimes for these to be more stable, we might have some neutrons that are left over. This is 3 individual neutrons, and then energy is going to be emitted through that process. And so this is what a fission reaction would look like. We would have one reactant, and then our products are smaller atoms or even neutrons, and energy with that. And again, a neutron, we just use a lowercase n, not uppercase, because uppercase is nitrogen. And a neutron has no protons and one, and the atomic mass is 1. And so that's how we would show a neutron that is on its own. So fission reactions, if we look at uranium-235, which was discussed above, if we have uranium-235, if there is a neutron that is going to be sent to hit the nucleus of that uranium-235, then we get that uranium-236 with that added neutron. And of the 2 nuclei that are formed from that split, we get barium and krypton. We get neutrons and then gamma rays in the form of energy with that. And so that is how a nuclear fission reaction occurs. And so certain isotopes are good for use as nuclear fuel in nuclear power reactors. Isotopes that are going to be useful are plentiful in nature, so we would have them available. They have long half-lives, so they are going to react, but they're not going to be radioactive on their own. They split upon neutron capture, so if a neutron sort of up here, once that uranium gets that neutron, that uranium-236 is going to split. And they release multiple neutrons during fission and create chain reactions. The most common nuclear fuel is the naturally abundant uranium-235. And so that is going to undergo a fission process in order for that energy to get collected, and then we can use that. Chain reactions, because this mentions that they create chain reactions. So it's saying that we're not going to just have fission happen one time and then we would have to start the process again. A chain reaction is when one fission reaction occurs and then sparks another reaction and continues that chain. And so that would be like if we look back up here, that maybe this krypton is going to go and it will start its own chain reaction so that we can release more energy as we go. And once the neutrons are released, then they are going to start new fission events. And so it's those neutrons being released, those can run into something else, and that's going to continue or kind of help keep that chain of reactions going forward. And so we can utilize chain reactions to harness more energy. So the controlled chains of reactions are what nuclear power plants use. Uncontrolled chains, though, are what are the chemistry that power atomic bombs. The nuclear disaster in Chernobyl was caused because a reaction became uncontrolled and massive amounts of energy were released. So we do have to be mindful when we're considering using nuclear power about the effects that it might have. So here are some uses. Again, power plants are going to use controlled nuclear chain reactions to produce energy and heat. The heat turns liquid water into gas, and then that steam is going to turn turbines, which are connected to generators. Currently, and I did not re-look up this statistic, it might have changed since I first made these notes. The United States uses nuclear energy for 18.2% of its total energy production. All right, here's a periodic table as we start to look at writing nuclear fission reactions. It's the same properties that we have used with our other nuclear reactions, but we can tell that something is fission when we have just one thing that is breaking up into smaller atoms. And again, we might have neutrons in there. And if we have that number out front, that's to show we have 2 neutrons, so we have to take that into account. So looking at this first one, we have that uranium-236. 92, that is the atomic number. So as we look at how can this be, or how is this equal, we need to look at what is going to go on that left side. So we have 236, and that's going to need to equal something plus 97 plus, we do have 2 neutrons, so plus 2. And however you like to kind of go through and do that math, we're looking at filling that piece in. So 97 plus 2, that's 99. And so if I do 236 minus 99, I get that 137 is going to be the mass I need in the top. Again, that's that total mass of protons and neutrons. Doing the same thing now on the bottom, 92 needs to equal something plus 40 plus, well, our neutrons don't have any protons in it, and so that's not going to contribute. So 92 is going to need to equal something plus 40. So if I subtract 40 from both sides, we get 52 down there. And I can go up here and look, what is my element number 52? It is tellurium, and so I'm going to put that Te here for that nuclear fission reaction. Looking at our next one, we've got one element that is breaking into smaller elements, which is the definition of fission. So we've got that 236, 144, and we need to figure out what is missing in this piece with 2 neutrons. So 236 is going to equal 144 plus something plus 2 neutrons. And so we can do 236 minus that 146 to get that this is a 90. Looking at my protons, 92 needs to equal 54 plus something. Our neutrons have no protons in them, so we're not going to take that into account. And so I'm going to have 92. Again, minus that 54 is going to tell me what other piece I need in there, and that is a 38. Going up here, finding number 38 is strontium, so Sr. on there. Looking at this next one, feel free to try this on your own if you want. 236, 146, 87, and then something. So we've got that 236 needs to equal 146 plus 87 plus something. When I add those together, I get 233. And so if I subtract that from that 236, I get 3. As I look at the numbers on the bottom, 92 needs to equal 57 plus 35. Well, 57 plus 35 is that 92. So I have no protons here, but I need a mass of 3 here. So we're actually going to show that with neutrons, and instead of having my 3 in that top number, I'm going to put that 3 in front. Because a neutron only has a mass of 1, so I'm going to need 3 neutrons in order to make up that mass for those neutrons that got released through that fission. And again, all of these release energy, so those neutrons are going to help the chain of reaction continue. The energy released is then going to be harnessed to produce usable energy. So that was nuclear fission. We also have nuclear fusion, and nuclear fusion is kind of the reverse of fission. Fusion is when 2 smaller atoms are combined into one larger atom. And this emits an enormous amount of energy, 3 to 4 times more than fission does. We see fusion because these are smaller atoms. Usually it is atoms with a mass of less than 60. All elements that are heavier than hydrogen would form via fusion in stars. And it requires really high temperatures, and so it's not a practical process for us to produce energy and to use it. So hydrogen plus hydrogen produces helium and emits enormous amounts of energy. And so that process of fusion here is kind of that, it shows this process here where we have 2 atoms that are then combining, and sometimes those can combine and just release energy, but this one is combining to produce a more stable particle, and any other neutrons might be released through that process. Fusion is what fuels stars, and so those stages of those stars are based on what step and what elements are undergoing fusion. Hydrogen burning produces helium, so the fusion of hydrogen atoms, when that is happening, those are stars that are considered main sequence or yellow dwarfs. As those elements get larger, so helium burning to produce carbon, so the fusion of helium to produce carbon, oxygen, and nitrogen, and magnesium, that would be a red giant. And so you can see here carbon with helium, oxygen with helium, neon with helium, getting to that magnesium. Those are the processes that form a red giant star. Elements through iron and nickel can undergo this process with helium to form red supergiants. And then all fuel is consumed until a dense core is created. And once that core collapses and elements break down, that's when we have a supernova. So our sun is currently in that main sequence yellow dwarf stage. So it is fairly young at 4.5 billion years old. And that process will continue as the universe exists. All right, and here is that picture of looking at these different phases for a star, and kind of how those fusion reactions occur. When those occur, energy in the form of gamma rays is produced as well, and we see that as light energy. Can we use fusion reactions to produce energy? Reproducing the temperatures and pressures that would be needed for fusion is extremely difficult. And enormous amounts of energy are needed to do this, which usually exceeds what the energy that we could get from it. And so obtaining electricity from fusion of hydrogen would be remarkable, but we are still a ways away from ever being able to do that in an economic fashion. Let's do some practice at nuclear fusion reactions. So as we look at this, we've got 24 plus 4, that's going to tell us the total mass that we need when that magnesium 24 and helium 4 undergo fusion. So 24 plus 4 is 28. And then we do the same thing with those protons. 12 plus 2 is going to give us 14. And then we can go to our periodic table, and silicon is element 14. And so we can fill in that symbol. And when those atoms undergo nuclear fusion, those produce silicon and release a large amount of energy. Feel free to try the next examples on your own. Next we have silicon 28 and magnesium 24. Those two need to add together. So we get 52. And then same thing with our protons, 14 plus 12. That 14 plus 12 is going to give us 26. And when I look at my periodic table, element 26 is iron, plus a large amount of energy is released. Last one, oxygen 16 plus helium 4, so that's plus an alpha particle. That's 16 plus 4, we get 20 for that mass. 8 plus 2, we get 10, and element 10 is neon plus energy for that last example of a nuclear fusion reaction. And we've discussed how energy is produced through these reactions. If we look at ranking from highest to lowest energy that gets released, well, what we just talked about was that fusion, and fusion is going to produce that highest amount of energy. After that is fission, and fission is actually what we use for nuclear power and in nuclear power plants with those chain reactions. Thinking back to this first set of notes where we have gamma, beta, and alpha radiation, well, alpha radiation is the weakest with that helium atom being released. Beta radiation is next. That's if we have an electron being released. And then gamma is that release of energy. That gamma radiation is strongest of those other three we talked about, and then comes fission and fusion. So all of these produce energy, but only some of them produce energy that we can harness and use. And we have not been able to figure out how we can use fusion to produce energy in a way that is sustainable. All right, here are just a few additional examples combining fission and fusion. If you want, try these on your own and come back and check your answers, or go ahead and do these with me. All right, so we have a magnesium atom plus a helium atom. So we have two smaller atoms combining to make a bigger atom, and so that is going to be fusion. How do we figure out what that is? Well, I'm going to have 24 plus 4. That's going to give me 28. That's the total mass. That doesn't tell me what element I have. But if I do 12 plus 2, which is going to give me 14, then I can take a look at my periodic table, and silicon is number 14, so we can fill in that symbol. All right, silicon 28 and magnesium 24 undergo fusion. Well, we already have magnesium 24 up here, so I'm going to have that 24. If I need to, I can look at my periodic table to figure out how many protons magnesium has. And then we also kind of already have that silicon 28 is the mass, and we just checked our periodic table that was 14. And those are undergoing fusion as well, so those are going to combine to give us that larger atom. And we get that 28 plus 24 is going to be a total mass of 52. And then I'm going to have a 26 here, which means that element number 26 is iron. So that's going to be Fe. And really, I forgot up here, energy, a lot of energy is released when this happens. And so adding that energy on the end to show that. All right. Now we've got uranium-236, which is a large atom, and it's splitting up into two smaller atoms, and we have some neutrons and energy being released. And so this is going to be fission, which releases the most amount of energy. And uncontrolled fission chain reactions are what cause nuclear explosions. We could also harness those nuclear chain reactions to collect this energy as well. So as we are looking at this 236, well, I know that that needs to equal this number, plus I have two neutrons. And so I'm going to go 236, and I'm going to subtract off 97, and I'm going to subtract off 2 to get that I'm going to have a mass of 137. And then I'm going to go ahead and do the same with my protons. 92 plus something is going to equal 40, and I have two neutrons, but neutrons don't have protons. So I'm just going 92. That needs to equal something plus 40, so that 92 minus 40 gives me a 52, and I can go to my periodic table and find element number 52, and so this is tellurium, so Te as that symbol. All right, and here's another uranium-236. Uranium-236 can undergo fission in multiple ways depending on how it breaks apart. So we've got that 236 on the left, so that's going to need to equal 146 plus 87 plus something. Energy doesn't have any mass. So to figure out what this something is, I'm going to go 236, and I'm going to subtract off that 146 and that 87, and I get a 3. Looking at my numbers on the bottom, doesn't matter what order, or if you do the numbers on the top first or your protons on the bottom first. I usually just start with my top numbers, but it doesn't matter. 92 is going to need to equal 57 plus 35 plus this. So let's do, I'm going to do 92 minus that 57 minus that 35, and I get a 0, meaning that whatever is here has a mass of 0 protons. And so, but I need, sorry, it has 0 protons, but mass of 3. Well, what has mass but isn't a proton? That is a neutron. And we go ahead and list those neutrons. I'm going to pull this 3 out front. Nope, I'm not. So that 3, we're going to make it a coefficient, and I'm going to put a 1 here because each neutron only has a mass of 1. And so we use a coefficient to say, well, how many neutrons do we have that are being emitted as that undergoes fission? All right, looking at our next one, uranium-236, again, undergoes fission to produce, this time it's producing xenon-144, an unknown atom, 2 neutrons and energy. And so we can go ahead and look at that. We've got uranium, that 236 again, that is a really unstable isotope. I just use that from up here. Undergoing fission to produce, well, we've got xenon, the mass is 144. Well, how do I find the protons? I'm going to go down to my periodic table, and xenon is number 54. So I'm going to fill that in for my protons. An unknown atom, I don't know what that is. 2 neutrons, so 2, and then we write a neutron as having that mass of 1, 0 protons, and then a lowercase n, not uppercase because uppercase is nitrogen, and energy. And now we have kind of that base reaction like we have up here, kind of that skeleton where we can fill in what we need. So I've got 236, well, that needs to equal 144 plus something, plus I have 2 neutrons. So I'm going to do 236 minus that 144 minus, I have 2 neutrons, and so that is going to have a mass of 90. And then same thing with my protons. Well, 92 needs to equal 54 plus something, and my neutrons don't have any protons in them. So just 92 minus 54 is going to tell me that I need 38 protons to fill in whatever that piece is. And so let's go and look what has 38 protons. oh, there we are, strontium. And so we would have that SR right there. All right, so fission and fusion, those are our last kind of two types of nuclear decay that we are looking at. There is a worksheet and a check-in provided. Reach out to your teacher with any questions.